3, and I'll be up and down. I sit here, but I don't really stay seated the whole time. I'm going to talk about functions quite a bit tonight, or this afternoon. I say tonight, this afternoon. Functions. And functions are based on mathematical relations. And that's just a correspondence between two sets. And the two sets that we are going to hang on to in this class would be the domain and the range. Domain being the x values, range being the y values. Another way of putting that would be x is the input and y is the output. Input and output on those things. Okay, so relations are the basis of what functions are. It's just a correspondence between x and y values for us in here. Okay. So another way a relation might be seen as a set of ordered pairs. Like you might have, 3, -2, another ordered pair 5, 6, and then -7, +8. That is a relation because it's a set of ordered pairs. Any set of ordered pairs is a relation, but it's not necessarily always a function. Okay, so let's get into what the lesson was about. Functions. A function from x to y, or into y, that's a better way of describing that. X into y is the way we're going to deal with functions in this section. What that is it associates each x with one y. It doesn't repeat x values. Okay. Doesn't repeat x values. And the way I teach this in high school, I tell the teenagers, they're all starting to date and all that fun stuff. And if you want to function properly, you don't repeat your x's. And that always catches them. And they remember that. So don't repeat your x values if you want to be a function. It's okay to repeat the y's. Okay, y's repeating is not a problem. It's x's that are repeated that tends to cause a lot of problems in life and functions. Okay, so we've all been there. We've all lived through it. So we're going to play the game. Is the relation a function? And we're going to see several different representations of functions or relations in general, and be able to recognize which ones are functions, which are not, and some of the representations, whether it be a set of ordered pairs, a mapping, or graph, depending on what picture we see, which one's the easiest ones to tell that from. So we're going to look at several different types. First one is the old boring set of ordered pairs: 2, 3, -3, 5, 6, 4, and 8, -2. And that's a set of ordered pairs, no doubt. Easily a set of ordered pairs. Is it a function? Why? All the x's only occur one time. No repeated x values. So that is a function. Easy peasy. Here's another set. -3, 7, 8, -1, -2, 7, 8, 0. Is that a function? No. Why? Those 8s are repeating. The 7's repeating. Does that matter? No, because they're what kind of values? They're y values. And it's okay to repeat the y values. Just don't repeat your x's. So it's no. And the reason being repeated x values. So repeated x value is the reason we can't call that a function. It is a relation, but not a function. Okay. So regular set of ordered pairs, real boring, basic things. The next representation we want to talk about is what's called a mapping. And a mapping is basically taking a couple of bubbles, a domain and a range bubble, and putting some numbers in there, 3, 5, 7, -2, and 6, and then mapping the domain value to the range value. And when they map that, they just draw an arrow. It's pretty boring, but 3 goes to 6, 5 goes to -2, and let's throw the 7 to the 6 as well. And what that really does create is a set of ordered pairs, but it's not represented as a set of ordered pairs. And the question still remains, is that a function? It would be, the domain bubble represents which values, x or y? X values. So none of them are repeated. So this would be a function. So this is a yes. Very boring thing here. Do another mapping. Range. 3, -5, 8, 7, -9, 10. So let's map the 3 to the 7, the 5 to the 10, the 8 to the -9, and then the 3 to the 10 as well. So would this be a function? Definitely not. You got that repeated x value there. Repeated x values. No can do. All right. So next thing that we could see would be a graph to determine if something is a function or not. And sometimes that graph is not even drawn for us. They may just say it's y equals 3x minus 2 and say, is that a function? Why or why not? Well, that's a linear equation. So I'm just going to sketch the graph of that, something we maybe know how to graph that. How would you graph that? Does anybody remember? Correct. Very good. So up 3, 1, 2, 3 over 1. So we get this line that's doing that weird thing there, and I don't have a ruler, so I'm not very good at drawing straight lines. But we get that picture going on. And there's a nice test when we have a graph. Does anybody remember the test that you can use? Yeah, vertical line test. If that passes the vertical line test, that means I can take a vertical line and I can place it anywhere on that graph, and it only is going to touch it in one spot each time. Okay. If I were able to place this vertical line on that graph and it touched the graph in 2 places at the same time, then it's not a function because that's a repeated x value. So this one passes the vertical line test because I can only, anywhere I put a vertical line, it only touches that graph one time. So it passes. So this is a function out of that. So yes. And don't forget the vertical line test. That's always a good thing. Remember that vertical line test. It's handy out of that. All right. Now, kind of a difficult one here. Just throwing this in there. Y squared equals x squared minus 4. It's kind of an ugly thing that they throw into this first section that we talk about because they squared both variables. And anytime you square both variables, you're creating repeating things happening. And if I were to do the math to get y by itself, how could I turn y squared into just plain old y? Take the what? Take the square root of both sides. And if I do that, I can't just take one side of the square root. I've got to take both sides, the positive and the negative side of the square root. And this is what's happening. But if I plug in a 2 for x, positive 2 squared is 4. 4 minus 4 is 0, right? Well, that only gives us one value because there's not a positive or negative 0. So that's okay. But what if x were 4? If I plug 4 in there, 4 squared is 16, minus 4 is 12, but I have the positive and the negative square root of 12. So that's two different y values for the same x value. So that creates a repeating of the x's. So anytime you see both variables squared, you know that that's not going to be a function. Okay, that's really the best thing I could tell you. It's not a function. No, it is not a function. If you were to graph this, I'll go ahead and just share that with you. If you were to graph this on the coordinate plane, it ends up looking something like a sideways parabola, and the top half is the positive side, the bottom half is the negative side. Would that pass or fail the vertical line test? It definitely failed the vertical line test. So that'd be another way to tell that if you weren't sure. Just using some graphing going out of that. Okay, so determining if a representation of a relation is a function. You got repeated x values, then it's not. If you can repeat y's all day long, but cannot repeat x's. That's what screws it up. Okay. All right, let's talk about function notations. Since we know what functions are, what they look like as far as a graph or a set of ordered pairs or a mapping. Let's talk about some notation that we use with functions, and that's called function notation. Fun stuff. Same section. Function notation. Remember that f of x is the same thing as y. G of x, h of x, k of x, whatever letter I call that function, whatever that is, it's the same thing. It's a more descriptive way of saying y, though, because it tells this is the y value for a particular x value, is what f of x tells us. It's the same thing as y, though. So it's like creating an ordered pair. So if you had, for example, we want to find f of negative 5 for f of x equals 3x plus 5, something real basic here, example G. What that means is it says, okay, f of negative 5. Negative 5 is now the what? X value, okay? So we're finding the y value for when the x is negative 5. That's what it's a very descriptive notation for that. It's not just say, hey, y is this, but where'd that come from? This tells us, hey, that came from taking negative 5 and plugging it in for x and working from there. It'd be negative 15 plus 5, which would be negative 10. F of negative 5 is equal to 10. Keep in mind that creates an ordered pair. That's an ordered pair, really. It's in function notation. The boxed in one's in function notation. But it is an ordered pair, just in function notation, that x is negative 5, y is equal to negative 10, is what that's saying. Okay, so function notation, really good way of describing y. Okay. Do a few more examples of finding some things. Here's our function, 2x squared minus 3x. Let's find f of 2x. Ooh, that's a fun one. So definitely brushing up some algebra skills as we go here. So what are we plugging in the place of x? 2x. Okay, so f of 2x means everywhere there's an x in this original problem up here, we're going to put 2x. 2 parentheses 2x squared, 3 parentheses 2x. And then we're doing math, so we have to follow what set of rules? Order of operations is exactly what we're going to recover here. So which one comes first? Parentheses. Okay, so we look in the parentheses. Is there any operation in the parentheses that we can do? No. So the next step, exponent. So There's an exponent on the 2x, so we're squaring 2x. What's it mean to square something? Times itself, right? So 2x times 2x would be 4x squared. And then technically I'm not doing that step yet. I could, but I don't have to. After we've done exponents, it's multiplication, division, left to right. Or those are the same level. It's left to right. So multiplying first 2 times 4x squared, 8x squared. And then negative 3 times 2x is negative 6x. And we found f of 2x. Can't combine those because they're not like terms. One of them's x squared, one's plain x. Can't put them together. All right. Easy. Let's take the same function, f of x equals 2x squared minus 3x. And let's find f of negative x. So throwing that negative sign in there. And seeing what we can do with that. And what that changes about the problem, or if it changes anything. Plug it in. 2 negative x squared minus 3 times negative x. What's negative x squared? Just x? Negative x times negative x would be positive x squared. It's really just 2x squared there. And then we can do the math here. Negative 3 times negative x would be negative times negative turns into positive 3x. And there's f of negative x. We found it. So finding function value, even if we're not given just a regular number, we can still plug it in there and work it out. It's not a big deal. It's just some algebra. All right. Now, with function notation, they can do some kind of funny things here. One of the things that they could do is give you a function, and let's just use the same one, 2x squared minus 3x. Doesn't matter what the function is. And they ask you to maybe find negative f of x. So it's not necessarily plugging something different in for x, but it's saying the negative of f of x. What does that do to everything? Well, what if it's already negative? Positive. Just change. That's exactly right. It changes the sign of everybody in the problem. So negative f of x is just like negative 1 times 2x squared minus 3x. And then just simplify that. So that's negative 2x squared, and that becomes positive 3x. And that's negative f of x. That's the math involved. It isn't necessarily something you'd have to show the work on, but that's what's happening. Changes the signs by multiplying by something. Let's do this one. Same function, f of x is equal to 2x squared minus 3x. And let's find 3 f of x. What's that mean we're doing? Multiply everybody by 3. Really easy stuff. They can multiply them by 3. 6x squared minus 9x, right? Distribute a 3 across the whole problem. That's all that means. Pretty simple stuff. Same function. I know it's getting boring because it's the same one over and over. But this one really gives us some good practice on this one. Let's find f of x plus 2. Nice. A bit more going on with that one. F of x plus 2 means we're plugging what in? X plus 2. Everywhere there's an x. 2 parentheses x plus 2 squared. 3 parentheses x plus 2. Okay. Now, again, order of operations takes control and says you got to do parentheses if you can do anything in them. Turns out you can on this one. The next thing would be exponents. So we got x plus 2 squared. So out here, I'm thinking x plus 2 squared. That's what that means. Anybody remember how to multiply that together? FOIL method. If you've heard of FOIL method, that's what that is. But it's just distributive property twice. X times x, x squared, x times 2, then multiply the 2. 2 times x, 2x, 2 times 2, 4. And then simplify that. I'm going to go put it right here. X squared plus 4x plus 4. And then we can go ahead and do the distributive property on the next part just to save an extra step here. Negative 3x minus 6. We already know that, but that's what's happening there. I don't ever teach FOIL method anymore. So if you learned it with FOIL method, first, outer, inner, last, that's what we did. But it's not necessarily, if it's a trinomial times a binomial, it doesn't work that way. So FOIL method is just distributive property twice. So that's the way I teach it now. All right, so distribute the 2. 2x squared plus 8x plus 8. And then we got the minus 3x and the minus 6. Last step is just combining the like terms, which is very easy. 2x squared. Then you got 8x and negative 3x is 5x. 8 and negative 6 is 2. And there is your f of x plus 2. Finding that function. Definitely easier when they just give us a number to plug in. That's always much easier to do than the algebra part, but still something we need to practice just to get back to going to there. Just a couple more in this section, and then we'll move on to something else with function notation, and then we'll move on to something else in this section. So first section is kind of long. The rest of them are not as long. So let's do one more of those. F of x, again, let's use 2x squared minus 3x, and let's find f of 2x minus 3. So a similar problem, a little bit different because of the coefficient. But work-wise, very much the same as far as that goes. So over here, I'm 2x minus 3, 2x minus 3. If you can do that in your head, yay, more power to you. But most of us can't, probably. It's just not something you practice a ton. But if you can do it in your head, you get a million make-believe points. And then just combine. Biggest mistake that happens when folks are doing this is not necessarily the not knowing what to do. It's forgetting to combine the like terms in the middle or canceling them out with the wrong sign or something. Sign mistakes are always going to be the most common mistake in every math class, from when you first start using positive and negative numbers in 4th or 5th grade, all the way through differential equations or thermodynamics if you're an engineering major. It's sign mistakes plague mathematicians. That's just part of it. But you just gotta be careful. 24x plus 18, 6x plus 9. Combine like terms. 8x squared minus 30x plus 27. F of 2x minus 3. All right. Easy stuff there. All right. All right. What I want to show you now with function, last thing with function notation is using that TI calculator to evaluate something for you without having to do all the math by hand and work that out. So example N is with the TI 84 plus. Technically, any calculator can do this, or any scientific calculator can do this as well. But f of x is equal to 3x squared. Change it up a little bit. F of 1.25. Something like that. Something that it wouldn't be easily done in your head. Squaring 1.25 is not easily done in your head. Then multiplying that times 3, not incredibly easy to do in your head. So the TI calculator can be helpful when we're only plugging in a number. It's very helpful for that. So with the TI calculator, there's a couple of different ways to use it. I want to show you the way using the graphing capability of it that it's really nice for that. So what you want to do is you've turned your calculator on. You're in the regular calculator screen. Press the Y equals button. Because remember, we're dealing with a function here. F of x is the same as y, so I could type in that function right here, and y1 is technically f of x. And I'm going to type in that function. So I'm going to type 3, and then the x is right beside the alpha button. Right there, it's highlighted in red right now. X squared, and the squared button's there on the left side. And then minus 5x and plus 7. So I put that into the calculator, into its y equals menu. If I wanted it to draw the graph of that, I could tell it to, I could hit graph and it'd draw the graph of that. And I could get any ordered pair on that graph I want. But I want to just get an ordered pair value. So what I want to do is go to the table. So I press second and then graph. And right now my table is created for me already. And yours may be as well. If it's not, you're actually ahead. But if your table is already created, like see how mine is, it's generated all these integer values from -4 all the way to +6. Those are the y values that go with it in the blue column. That's great, but that's not the numbers I need. I need to be able to type in 1.25 and get it to spit out the y value. So in order to get your calculator to do that, and this is something, once we set our calculator to do this, we don't have to do it again. It works like this from here on. We want to press second window to go to table set. And we want to set the independent variable to ask. So second window to get to this table setup menu. And then set independent, that's the x value, to ask. So you just arrow over to ask and hit enter. And it'll darken it in. And you should be ready to go. Now I want to go back to that table, so second graph, and you'll notice that I don't have any values anymore. They're all gone because it's waiting on me to ask what to do. So I'm going to type in my number, 1.25. And it gives me the y value back to it, 5.4375. Great if you're just plugging in a number. Not if you're plugging in like x plus 5. Doesn't work. Calculator can't do that for you. Or this calculator can. There are some that can. This one is not one of them. It's not legal to have one that can do that for you for this class. Anyway. All right. Okay. So we've talked about function notation. We've talked about what makes a function. Now let's talk about the domain of functions. So domain of functions. Still in section 1. Like I said, this section is a really long section. The other two that we'll cover tonight are not nearly as long. They're much easier. This one just got a ton of stuff in it. Domain of a function. Or of a function. Okay. That's the x values that quote unquote work for a function. Okay? X values that work for a function. And by work, I mean don't cause division by zero or some sort of weird thing to happen, like the square root of a negative or something like that. We can't have that weird stuff happening. That's what doesn't work in math. Okay? So X values that work for a problem is the domain of the function. The Y values that go with that is obviously the range of that function. But domain starts with a default. With all real numbers. And there's a thing called interval notation that we'll work with. And depending on who you had for high school math or who you have for high school math right now, how much interval notation experience you may or may not have. You'll get plenty in here, because we do a lot with interval notation. Okay? The interval notation for all real numbers is negative infinity to positive infinity. Okay? Thank you, tattoo parlors, for making the infinity sign part of everyday language again. There's a lot of those right now. Okay, so the infinity symbol is something we're familiar with. Okay, so interval notation starts with that. That's the default. What we're going to be looking for are things that carve that out, that cut out some of those numbers. And those things are red flags. I'm going to use red flags. The first red flag that comes up are x's in the denominator. Okay. I always, when I talk about this with high school kids, I talk about, you always got to know who you're dating, who their exes are, because that's in the denominator of who they are, and it kind of, they come up every now and then. Sometimes it causes weird things to happen because something happened with an X, if it's in their denominator. So X is in the denominator, cause weird things to happen. They cause division by zero. And what's the only number in the world we can never divide by? Zero. We can't take your McDonald's Coke and divide it into 0 pieces, right? We can divide it into 2 pieces or split it with somebody, right? But you can't divide it into 0 pieces. So that's why we can't divide by 0. X is in the denominator cause us to have division by 0. So we gotta look for that red flag. That's the reason that's a red flag, is division by 0. And that'll come up, and we'll see how that happens. The other red flag, he said the other. That means there's only 2. The other red flag are square roots. And when we're taking square roots, what kind of square roots make weird things happen? Negative numbers in there. If there's a square root of a negative, that's where that imaginary number system comes, or the complex number system comes from. For that I comes back into the work, and that always makes it weird. So if we're dealing with functions, if we have a square root with a variable inside there, we need everything to be positive only. We can't have a negative inside the square root. So that's going to be a red flag, is if we see square roots, we see a variable inside of that square root, we got to think, okay, things inside of that square root can only be positive. So that's going to affect our domain. If neither of these red flags exist in the problem, the domain is all real numbers, or negative infinity to positive infinity. They mean the same thing. We're going to list both of them today as we're doing this in what's called set notation and then interval notation as well. So we're going to try to list that. So no red flags, it's all real numbers. Red flags, we got to do some stuff. Okay, so let's look for those things as we go through some examples here. So we want to state the domain of the function. Example O, donut, f of x. X squared plus 5x minus 7. So a nice little quadratic equation there. Let's think, are there any red flags? The red flags could be an x in the denominator. Are there even any fractions here? That can't be a red flag then. Are there any square roots? No. So it can't have either of those red flags. So this means it has no red flags. So because there are no red flags, and I'm just writing this down so that maybe that helps us remember. There's no red flags. The domain would be x such that x is a real number. That's set notation. So this is set. Interval notation, interval. My R's and P's. Sorry about that. Came unplugged here. There we go. Interval notation, negative infinity to positive infinity with parentheses around it. It looks like an ordered pair, but it's interval notation. That means every x all the way toward negative infinity and every x all the way to positive infinity work for this problem. There's nothing that screws it up. Okay? This one is perfect. It's got a domain that's all real numbers. Not that the ones that don't have a all real number domain are imperfect, but they're just different. Kind of like math teachers. We're just different. It's okay. All right, so let's look at this one. Cube x. 5x over x plus 3. I see a fraction. So that tells me, look at the denominator. Look at the denominator. What's going on? Is there a variable in the denominator? Yes. That's a big red flag because we got a variable in the denominator. If there's a variable in the denominator, what is the only number we cannot divide by? 0. So what number would make that denominator 0? Better math question is, when is x plus 3 equal to 0? At negative 3. Just by solving that equation. When x is negative 3, we got a problem. That's what's happening. So what that means is for our domain, in set notation, curly brace, x, straight up and down bar, that means x such that we've got to tell it that x can't be negative 3. It's any number except for negative 3. That's the only one we can't have because it's the only one that would give us a 0 in the denominator. That's the problem that happens. In interval notation, and this is the one that most people are not as good at interval notation starting off because you just haven't done much with it. Interval notation, we got to think, okay, how do I carve out a negative 3 from negative infinity to positive infinity? Well, you think about you're riding along the x-axis of numbers, and you start way over here, you get to negative infinity, you're way over here, and you're riding along, everything's going good. I got to 0, or I got, here I'm like at negative 10, and I keep walking, and then there's this big hole here at negative 3. I've got to skip that. Okay? So I'm skipping negative 3. So what I've got to do with my interval notation is I say, okay, I started at negative infinity, and I ride along the train, I keep going, and there's this big hole in the tracks at negative 3. So I say negative 3, skip it, parentheses, skips it. And then we got to jump back on the track right after negative 3. And ride all the way to positive infinity. Okay? So this is skipping negative 3. It's negative infinity up to negative 3. The parenthesis says we can't touch negative 3. It's a big hole in the track. Then a U for union. Let's set through your stuff. Parenthesis again, we're starting right after negative 3. That's what that means. And we're going all the way to positive infinity. Okay? And that's the best way I could represent interval notation to you. Just think about riding a train and then you got to jump some spots or running along a track. You got to jump. Okay? Jumping uses parentheses. Okay? Jumping uses parentheses. That's what you got to remember. All right? Let's do another. H of x. So a different function. 12 over x squared minus 16. This is a fun one to do. We got a plain number up top, and then we got x squared minus 16 in the bottom. Is there a red flag for this one? Definitely. Definitely red flag. Got an x in the denominator. So to find out what values for x cause the problem, set the denominator equal to 0. How do you solve x squared minus 16 is equal to 0? Yeah, you could add 16 to both sides and use square roots. That would work fine. If you wanted to use factoring, you could do that as well. If anybody remembers how to factor. I like taking the square root there. That's a fun one. What's the square root of 16? Plus or minus 4. That's a big part of that. It's not only is positive 4 times positive 4 16, negative 4 times negative 4 is also 16. So we've got two numbers now that cause a problem with this one. Positive 4 and negative 4. All right. So set notation, gosh, it's so easy. Because you just say x such that x is not equal to negative 4 and x does not equal positive 4. Or you could say x such that x is not equal plus or minus 4. I would take either of those. I don't care which one you write. Okay? I would take either of those. You're probably going to see the first one more like on Canvas quizzes. That's how the program I use we tend to do that. Okay? So that's set notation. Interval notation. A little bit more difficult. But interval notation tells you a ton more. So where do we start with the interval notation? Negative infinity. We ride along the x-axis of negative infinity until we get to what number? Negative 4. And we skip it. So parenthesis. And then we ride from negative 4 till we get to what number? Positive 4. And we skip it. And then we go to positive infinity. So there's the interval notation for that. Much more difficult, but it is far more descriptive when you talk about a function. This one just tells you two things that x can't be. This tells you got all these x's from negative infinity up to negative 4. Then you got all these x's from negative 4 to positive 4. Then you got a whole bunch more after positive 4 up to positive infinity. So it really is a lot more descriptive and really nice and easy to look at. Okay, so variable in the denominator, red flag, set that denominator equal to 0, solve those things, get the values that x can't be. All right. Excuse me. F of x is equal to the square root of 2x minus 6. Red flag, square root with a variable inside of it. That means we got a red flag. What kind of numbers can we take the square root of and not make something weird happen? Positive only. So we need to know when is 2x minus 6. When is that positive? Excuse me. Well, how do I represent positive in math? If a number is positive, what do we know about it? It's greater than 0. Can I take the square root of 0? What's the square root of 0? 0. So I can take the square root of 0. And I didn't get an I, right? I just got 0. So it could be 0 as well. It's positive and 0 that we can deal with here. So here we have 2x minus 6. When is it greater than or equal to 0? That's going to tell us our domain out of that. So we just solve that using those skills that we have. Divide by 2. Greater than or equal to 3. So our domain in set notation, be all x's as long as x is greater than or equal to 3. Set notation is super easy. It's not hard. The interval notation is still not hard. What's the smallest number that we could have for this problem for x? 3. So that's where we're going to start. Instead of starting at negative infinity, we're starting at 3. Is 3 included when we run? Yeah, there's not a hole. Say it again. Yes, a square bracket. That's exactly right. Square bracket means include that number, and then we're going to go all the way up to positive infinity. And you never can put a bracket on infinity because you can never get there. Because if you think you got there, take another step. You're not there. And keep going. So bracket 3 to infinity is what x is greater than or equal to 3 means. Okay? Not very difficult there. Pretty easy. Trying to abbreviate a little here. Getting a little, you guys seem to be handling this absolutely wonderfully. G of x is equal to 8 minus 2x and then plus 7. Trying to make it very clear that the plus 7 is not inside of the print of the square root. Okay. Now, where's the red flag? In the square root, not the plus 7. It has absolutely nothing to do with the red flag. The red flag is only there. So that's the only part we worry about, being a positive number or 0. So we set up our inequality, 8 minus 2x greater than or equal to 0. That 7 really doesn't do anything to it. It actually has more effect on it has absolutely all the effect on the range, not any on the domain. And we solve that. So here, when we're solving this, subtract 8. So that's negative 2x is greater than or equal to negative 8. And then I divide by negative 2. When I divide by a negative with inequalities, what do I do? There's a rule. Yeah, flip that symbol around anytime you multiply or divide by negative. So some basic algebra stuff that we make sure we review that. Once you get the inequality solved, you're good. You just set up your domains. Set again is super easy. It doesn't affect the domain at all. The only thing that's affected the domain is the square root. This plus 7 has a lot of effect on the range, but it doesn't have any effect on the x, because the x is really kind of isolated inside of the square root symbol. Even if that 7 had an x on it, it would not have any effect on the domain. The domain is highly affected by that square root. All right, good question. Interval notation for x is less than or equal to 4. Well, what's the biggest number we can have on this one? 4. And everything is smaller than that, right? X is less than or equal to 4 says everything's smaller than 4. So negative infinity is definitely smaller than 4. And that would be the domains in set and interval notation for that. All right. Now, the last one of this section, we'll take a little break after this, get a little breather. Let's find the domain for k of x when we have square root 2x plus 10 over x minus 7. weird one. Because why is this so weird? It's got two red flags. It's got a red flag up top and a red flag on the bottom. We got a variable in the bottom. We got a square root in the top. So there's two red flags happening. So we got to do twice the work, right? That's okay though, because we're good at it. Which part y'all want to do first? Square root or the other? Square root. I always like to do the inequalities first, just because they're inequalities. They're different. So we need that top part to be greater than or equal to 0. So we just set that up, 2x plus 10 greater than or equal to 0. Solve that. So that'd be 2x greater than or equal to negative 10. X is greater than or equal to negative 5. Okay. So we got that going on. That's taking care of the numerator. The denominator, what do we do for that? At x minus 7, we do what with it? Set it equal to 0. So x can't be 7. What that boils down to. So our domain is the combination of these two things. We've got x's that are greater than or equal to negative 5, but then 7 can't be that. Is 7 greater than negative 5? Yeah, so it's in that spot. So it really matters. So when I do my domain, set notation, again, it's the easy thing. It's x is greater than or equal to negative 5, and then a comma, and say x does not equal 7. Set notation, super easy. The interval notation, a little trickier, because you got to think, okay, x is greater than or equal to negative 5. What's the smallest number I start with there? Negative 5 is smaller. I'm going to start with it. And I go up to what number? Positive 7. And then I got to skip it. And then I keep going to infinity after that. There's my domain for those, for that particular problem. Now, one last thing before we take a short break. If the square root is in the denominator, what part of the inequality do we lose? I heard somebody say it. Did you say it? You didn't say it. The equal to, why? The equal to part is the part we lose. Why do we lose that on the inequality if it's in the denominator? If the square root's in the denominator? Right, because the denominator can't equal 0. So that's where there's a little exception to that, is if you've got a square root of a variable in the denominator, you lose your equal to part. It's just strictly greater than 0. Okay, so that's a pretty important thing to keep in mind. I'll go ahead and write the suggested problems out of this. Again, this is not something I'm taking up, but it's just some problems from this section that would be, like what we're doing here. Be problems like will be on the Canvas quiz type thing. So that'll get you a little bit of practice with that. And